that simple ritual. Audible? Am I audible? Screen visible?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Great. So let's summarize what we did in our previous class. We discussed about the subgroup H of G, and as you can think of, H is the next letter after G, so that is why it is given this name subgroup. I mean, those of you who can think of why H. And then the cosets of subgroup H, we discussed about the left cosets and the right cosets. Whatever we are doing with the left cosets will be applicable for the right cosets also, but it will have its own set of basically things. Yeah. Then the cosets themselves can't be subgroup except for H itself or E times H, which is the identity element. But remember that the identity element is already there in the subgroup. So any element which is already there in the subgroup, if you multiply that or take a composition of that with subgroup, of course, it's nothing but the rearrangement of that subgroup itself. Yeah. So for any other X which is not in the subgroup, we will have left coset XH, which will have an intersection with H giving phi, that is no element in common. And then the number of elements of XH is same as the order of the subgroup H. So important. Then any two cosets XH and YH, either they contain same elements, that means that XH is equal to YH, or else no elements in common, that is XH intersection YH is phi. So what we get in essence is that the cosets partition the entire group into disjoint union, so that the entire group can be written as H union XH union YH. And what is meant by disjoint? It is just that the XH intersection H is phi, YH intersection XH or YH intersection H, that is phi. So that is the disjoint word here. So this is what we were doing. In today's class, we are supposed to do the Lagrange theorem. Then I will come to normal and factor subgroups. And finally, I will come to classes. So let's start today's class with Lagrange theorem, which is an extension of this topic of the cosets. Now that we know that the cosets divide the entire group into disjoint union, the important theorem which is emanating from it is that the order of the group G, which is represented with mod G, it is an integral multiple of the order of the subgroup H. So if there exists any subgroup H, then that will divide the group in an integral manner. There cannot be non-integral division. So if the group is, for example, of the order 10, then the subgroup can be of the order of 1, which of course divides 10, 2, which divides 10, 5, that divides 10, and then there is nothing else. 3 doesn't divide 10 and it gets integer. Yeah. So this is the importance of the Lagrange theorem. And let's just see, I mean, it is a natural extension of what we were doing, but let's just do it for the sake of completeness, that why we are saying that this happens. So in order to understand that, let's just think about, of course, think about the proof. So let's say there exists subgroup which is contained in a group, right? And the order of the subgroup is A mod H and this order of the group is mod G. So let us consider, so let's say this is my group, entire group, and let's say I have considered H here. Yeah. Now think about any element X, let's say, which lies outside my subgroup. So let's think about X does not belong to H. Yeah. So can somebody tell me what will be the number of elements in XH?
So mod of H.
Mod of H. Will XH be same as H itself?
No.
Remember, it cannot be because X
No,
lies
sir.
outside this subgroup H, right? So that means remember that H intersection XH is equal to phi. We have to just remember this. So now think about it. H union XH. So if I now think about H union XH, how many elements are there in this? How many elements in this union?
Mod H plus 1.
Mod
No, it will be mod H plus
mod H.
mod H. It will be twice mod H. Sorry, twice mod H. Yeah. So in case if it would have happened, if that H union XH is such that the G is exhausted, that means if we would not have left with any other exhausted, okay, I'm sorry. If G is not left with any other element, so somehow that H union XH, that is the only number of elements if it is there, then how many elements would be there in this group G? There will be 2H elements which are there, 2 times mod H elements which are there in this group G. In case if G is not exhausted, then what will happen? If G is not exhausted, that means that there are still some elements left. So let's say there exists Y. Yeah. तो अब अगर मैं YH बनाता हूं, so how many elements are there in YH?
So mod of H again.
So this will have mod H, and remember this will also have intersection with which is phi. Yeah. So you will find that in this case either YH is same as XH or it will have no elements which will be in common with XH. That is what we did last time. So that means in this case our union goes like H union XH union YH. So in this case it will go like this, and how many elements will be there in this case? How many elements?
Thrice of mod H.
Right, thrice of or 3 of mod H. So in this way you can think about our previous figure which I tried to make here, and this is why I actually structured it like this. So now you can think about something like Y coming out another set, let's say group is still not exhausted. You can think about another possibility that Z exists, so on and so forth, P and Q. Finally, the group will be exhausted, let's say even if it is a larger group. But the interesting aspect which you are seeing, that G will always be written as the XH union YH union ZH, so on and so forth, which means that the every time we are counting the number of elements after adding one more disjoint union, it will only be the integral multiple of it. So we can write something like K times mod H, where K is a positive integer, which basically gives us this point that mod G over mod H, the number of elements in the group, divided by the number of elements in a subgroup, can only be a positive integer and nothing else. And this was the statement of the Lagrange theorem. Lagrange theorem is a natural interpretation of the cosets formation. Why did we initially come up with this idea of the cosets? So that now we have this interesting theorem that the group can only have subgroups which are of the order which will surely divide mod G. It won't leave any remainder out of it. Questions here?
So what is the meaning of this exhausted? G is
Exhausted means
G.
if the G is completed. I mean, if there is no other element which is left after you take the union of H union XH. If no other element is left, तब आपके ग्रुप में कितने एलिमेंट हुए? टू टाइम्स मॉड H, राइट?
Yes.
तो आपका सबग्रुप जो था वो इस तरीके से था कि उसके अलावा जो पॉसिबिलिटी है लेफ्ट कोसेट बनने की, उसमें बस और एक मॉड H बनेंगे, उसके अलावा और ग्रुप में एलिमेंट्स ही नहीं है. So exhausted means that the group is completed. There are no members of the group which is left over. You get the main point, right? I mean, if it is not exhausted, then it. So ऐसा कभी नहीं हो सकता कि आपका exhaust नहीं हुआ है और कुछ fraction of elements बच गए. That is the interesting thing which is coming out. ऐसा नहीं है कि मतलब हर एक subgroup में चार बचे हैं and then suddenly जो बचे हुए element है वो दो बच जाएं. This is the importance of this coset formation and the knowledge that cosets either contain the same elements or either completely identical, or otherwise they will give you a completely different elements. No elements in common. तो ये जो दो चीजें एक साथ चली कि एलिमेंट्स कॉमन नहीं हो सकते और यूनियन जैसे जैसे हम करते जा रहे हैं वैसे वैसे आगे बढ़ते जा रहे हैं. सो दिस इज इफ यू कैन थिंक ऑफ द वर्ड डिसजॉइंट विच गिव्स द इंटरसेक्शन एंड वर्ड यूनियन, दैट एज यू आर मूविंग अहेड आपका ग्रुप फॉर्म होता जा रहा है मॉड एच से. सो आप मॉड एच से अपना ग्रुप फॉर्म कर, सॉरी मॉड एच से मॉड ग्रुप फॉर्म कर. सो द टू थिंग्स विच मैटर इज दिस. या okay, but the corollaries are very now interesting. So now think about this. If I ask a question, order of each element of a group G. So आपको हमने एक करा था order of a group and order of the element. Remember, order of the element can be of many numbers, whereas the group of course will have a unique number. Yeah. So now can I ask you what could be the possibilities for order of each element of a group G? So let's say group G has 6 elements. So mod G is equal to 6. What is the possibility of order of each element?
Sir, 6 or less than 6.
So but less than 6 कौन सा? 5 हो सकते हैं, 4 हो सकते हैं, 3 हो सकते हैं, 2 हो सकते हैं, 1
Sir,
हो
only
सकते हैं.
even. Sorry, sir, only even.
Sir, 0 to 4.
So what divides 6 completely? 1, yes.
2 and 3.
2, yes.
3.
3, yes. 6, yes.
6.
Only these numbers divide 6 completely, which means the only proper subgroups for each element can be 2, 3, and the only possible order of the subgroups can be 1, 2, 3, and 6. There cannot be any 4, there cannot be any 5 in between. In fact, this gives a very interesting power to you. If I ask you, give me, okay, give me, I should not write, possible subgroups of G if, let's say 1, mod G is 24. Possible subgroups. What are the possibilities? 1, yes.
2.
2, yes.
3,
3, yes.
4.
4, yes.
6.
6,
6,
8.
8,
8,
12.
12.
12, and
24.
so you see suddenly that you get this extra power, that earlier you were not clear that how many subgroup orders are possible, but now you are clear the only possible subgroups can come which will completely divide my original one. Okay, let me just give you another one. 7.
1 and 7 only.
1 and 7, but these both are what? They are the trivial subgroups. So what about the proper subgroups?
No one.
No one. So that means that 7, remember what is the interesting thing about the 7? It is
Prime number.
it's a prime number, and prime numbers are those which are divided either by themselves or by 1 and nothing else, right? So now comes an interesting portion. A group of prime order. Now आपको इससे दोनों बस पिछले स्टेटमेंट्स पढ़ने हैं and you should be able to answer. Is always what?
Trivial.
Yeah, trivial surely. That is always sure. But there is something more than that. What kind of groups we have read? So we started with group. Then we said that there exist abelian and non-abelian groups. Then we did cyclic groups. What are the cyclic groups? Cyclic groups are those groups which are generated by a single element. When we are saying single element means what? That means that I can always write this group as of the form G such that the group has G square composition, G cube, so on and so forth. Gn is equal to E. right? I mean, this is what the cyclic group was, that all the elements of the group were generated by a single element G. Yeah. Now, this is an interesting thing which comes about the prime groups or prime order groups, that the only possibility for this is cyclic and nothing else. Now, why this would be? Now, think about it. Let's say there exists something, even though the group is mod G is 7, so it's a prime one, and I can have an element which is G cube is equal to E. Then what is the possibility? Then that means that is happening in this group, that there exists a subgroup with G square G cube, only these 4 elements, right? But such a subgroup of order 4 is not possible for a group 7 because of Lagrange theorem, right? So that means this possibility that any element of the group has the order which is less than this prime order is not possible, because then that will go against the Lagrange theorem. So then let's think about it, that you have rest of the elements like this, but this guy is not possible because of the Lagrange theorem. Lagrange theorem says that only possible order of the subgroup will divide this number mod G completely, and 3 doesn't divide it, 4 doesn't divide it, 5 doesn't divide it, even 6 doesn't divide it. So the only possibility for this group is to be a cyclic, and this is a natural consequence of our Lagrange theorem. And remember that the cyclic groups are always abelian. What is meant by abelian? Let me just ask you.
4 fold properties plus commutative.
Right, that the group obeys commutative property for all the elements which are existing in that group. Yeah, okay. Questions here? No, okay. So I should give you a homework question here, that let's write down D4 group. Now, what is D4 group? Can anybody just suggest me?
Dihedral.
Group. What was D3? Equilateral triangle. What would be D4?
Square.
Quadrilateral.
Not quadrilateral, it has to be square. Remember, it was the equilateral triangle with which we started. So this will have 4 vertices. The last group had 3 vertices, the equilateral triangle one. Yeah. So first, find all symmetries. And you will find, of course, rotation symmetry and flip or reflection symmetries. Yeah. B, find, of course, after that, the order of the group. C, what is the possible order of subgroups? Can anybody tell me how many elements would be there? What would be the order of this D4?
8.
8. Excellent. And how many rotations? How many flips? Reflections?
4 4.
4.
4 rotations. 4.
4 and 4. So mod G will turn out to be 8. So will you be able to tell me possible order of subgroups?
1,
Yes, sir.
1, 2, 4, and 8.
Okay, very good. So then try to figure out all the possible cyclic subgroups. That means you'll have to figure out the element order. Yeah. Then I will not exhaust. I will say that for a subgroup, whichever subgroup you take, or you take all subgroup, for all the left cosets and right cosets, which is what we have done. And finally, I will ask you to make multiplication table. Why I have given you this question? This question has all the elements of what we have already done. We have already done D3 composition, so you should be able to follow this question. I mean, you should be able to do this question by following what we have already done. If you are getting stuck at any point, then you are going to revert back to me, sir, ये concept फंस गया था. So please explain this portion. Okay, question on the question which I have given, or questions on the question. No.
Sir,
Okay.
the D
Yes.
parts.
D part, form all cyclic subgroups. That means आपके पास जो एलिमेंट्स आएंगे, हर एलिमेंट का ऑर्डर आपको देखना होगा, राइट? और अगर आपको ऑर्डर दिख जाएगा एलिमेंट का हर एक का, तो आप उससे उसका साइक्लिक सबग्रुप बना सकते हो. फॉर एग्जाम्पल, इफ यू जस्ट थिंक अबाउट D3 subgroups, this one, you already find that L1 square is equal to E, which was the reflection. Remember equilateral triangle about A. It was same for L2 square equal to E, L3 square equal to E. So you can quickly form a group that means L1 and L1 square. So that is a subgroup which you have formed, right? And this subgroup is a cyclic one because it is generated by a single element L1, nothing else. So form all of these. So इसका मतलब है L2, L2 square, L3, L3 square, and then you'll have to think about rotation also. Any other question?
So in E part for the cosets, I have to multiply by the elements of the group in
Yeah,
all
so
the
you will have to select one H at a time, and then you will keep on multiplying from the left all the elements which are remaining, because if you are just going to multiply the same element, it is not going to give you different one, right? And then
Yes.
just do the same thing from the right hand side.
Okay, sir. Okay. Got
Yep,
it.
good. Yeah, do this, and this will have basically all the things which we have done. So I come to next thing, something which is again very interesting, which is called normal subgroups, and I will denote this by N. So since it is a subgroup, of course it is H surely, but it will have some other property which will actually qualify it to be called normal subgroup. Before reaching there, I must say one sentence very especially, and you must take that sentence very carefully. Listen to that. If you do not understand it, you will ask this question on it. Lagrange theorem definitely reduces the possibility of the subgroups, order of the subgroups. ऐसा नहीं कुछ भी सब order हो सकता है. Only those orders जो कि completely divide कर रहे हैं. But it does not mean कि उस order का subgroup exist करेगा ही करेगा. So let's just think about it. 12 के हमने अभी काउंट किया 1, 2, 3, 4, 6, 12. तो तीन proper subgroups 2, 3, 4. In fact, another one 6. So 4 proper subgroups 2, 3, 4 and 6. बट लैग्रांज थ्योरम ये नहीं कहता है कि 2, 3, 4 एंड 6 को एग्जिस्ट करना ही होगा. इट जस्ट सेज दैट द ओनली पॉसिबिलिटीज आर 2, 3, 4 एंड 6. देयर इज अ पॉसिबिलिटी फर्दर दैट वन ऑफ द सबग्रुप मे नॉट इवन बी एग्जिस्टिंग. लेट्स से 6, द ऑर्डर 6 मे नॉट इवन बी देयर. सो लैग्रांज थ्योरम का जो मेन मोटिव है, इट इज ओनली अबाउट द पॉसिबिलिटीज ऑफ द सबग्रुप. इट डजंट मेंशन दैट द सबग्रुप हैज टू एग्जिस्ट. We have to actually check it in a particular group whether that particular subgroup exists or not. Is it understood?
And sir, how can we check it?
Oh, you have to check the properties. Remember, subgroup को कैसे check करते हैं? Either you
Alright.
check it G inverse H, or you just check all the three properties. Remember, this is what. So now comes to something called normal subgroup. A lot of people, I mean, this depends on book. Some older book also calls it invariant subgroup. Now, what is this? This is interesting. If left coset, again coming from the code, is same as the right coset. So in general, for a group, remember the commutative property does not hold true. But if for some group, the left coset by an element is same as the right coset for that element, and if this happens for all x belonging to G, in that case, this particular subgroup H is called N. And there is another notation. Okay, I mean, this is mathematicians notation, but okay, even if you do not remember it, it is fine. You need to remember this concept. Left coset has to be equal to right coset. Now, generally, whenever I write it, what students think of, that if I am writing elements like H2, H3, so on and so forth, and I am writing like H1, H2, H3, so on and so forth, X, then it automatically means that H1 has to be equal to h1x. That's not what I am asking for. No. But I am saying that this x h1 can be same as any other element, maybe hj times x. But such that the entire group of these elements which are formed here on the left hand side will match the entire group of elements on the right hand side. So that is why please look into it very carefully that I am writing capital H, that the total elements, that the elements which are there on the x edge is same as the elements which are there in the hx. It does not mean that x h1 is equal to h1x. It can mean in fact x hi is equal to hjx for any hi hj belonging to of course h. Yeah, and these groups which obey this property, they are called normal subgroups. Now, just to have an example, that means let's just try to figure out. So let's take, we have already done a group which is, let's say, G multiplication 1 minus 1 I minus I. Let's take a subgroup which you guys gave to me earlier, 1 minus 1. Now question, so this cross which I am writing, of course it's a multiplication of the complex numbers. Now tell me whether all the elements are going to obey this in this particular subgroup. So what are the elements which are left besides 1 and minus 1? I and minus I. So can you tell me IH is same as HI or minus IH is equal to same as minus HI? So what will be IH? It will be I minus I. Yeah. What will be HI? Again it will be same. I minus I. So is it same? Yes, it is same. So let's just check it for the next element. Minus IH. You will find out that the same thing will happen. Yeah. So can you now say something about this subgroup H 1 minus 1 of the group G 1 minus 1 I minus I under complex multiplication? That this group,
It is a normal subgroup.
this is 1 minus 1 is a normal subgroup of G. So in this case, it's a custom to denote it by N. N is for all practical purposes, it is H. It is just that it will also obey one more property. Now, this is giving something interesting. Can you say something about the abelian groups, abelian subgroups of G? How do we define abelian group?
What it is, the
Left is same as the right one. So in the case of abelian subgroups, this will always hold true that the left cosets will be same as the right cosets. So the abelian subgroups are always normal subgroups by default. Yeah. So that's something interesting which is there, that the cyclic groups are always abelian, abelian groups are always normal. So these are some of the properties which are coming naturally, again by extending the concept of cosets. First the Lagrange theorem, now normal subgroup. In fact, this is now becoming even more interesting. Why? I can actually now think about something even further. What do I have in mind? Let's just think about it. So let's consider the same group, same normal subgroup. Now we know that H is the normal subgroup 1 minus 1, and we will form all possible distinct cosets. Okay, so what do I want to do? I want to form all possible distinct cosets for this one. So 1, of course, 1 minus 1 itself, I can just call as K1, which was my normal subgroup, which is I am calling as the first coset. What is the other possible cosets which is possible in this? So if you take I times n, it gives I
I minus I.
minus I, right? So let's call this as K2 because this is different from 1 minus 1. What about minus I times n? What is minus I times n? Is this a new coset or it is the same?
It's same K2.
The same.
It's same as K2. So I am not going to count it as a different one because I am interested in figuring out all possible distinct cosets. In fact, what you will find that there exist only two cosets, K1 times K2. So two possible distinct cosets. Fine. Now I defined interesting word called composition or sometimes also called coset multiplication. So let me just define that. I define a composition or this as such that K1 composition K2, so I'm coming up with a binary operation, it is going to give me, so let's think, 1 minus 1 was my K1, I minus I is my K2. So I will multiply all possible combinations. 1I, 1 minus I, minus 1I, minus 1 minus I, and retain only those elements which are distinct. So retaining only distinct elements out of all possible compositions. So 1 into I will give you, let's say I, 1 into minus I will give you minus I, minus 1 into I will give you minus I, minus 1 into minus I will give you I. But okay, this element has come again and this element has come again. So I am going to retain only once I minus I. Now I minus I is itself a coset. Which coset it was?
K2.
K2. Great. So we have defined a coset multiplication here for a normal subgroup such that the coset multiplication will consider all possible multiplications and retaining only the distinct elements. So can you just give me what will be K1 composition K1? So 1 minus 1 composition with 1 minus 1.
K1.
X. Excellent. You have given me K1. What about K2 composition with K1? So I minus I first and 1 minus 1 afterwards.
K2, sir.
K2. So of course the group itself is abelian, remember. So it will not give you anything new. Let's do something interesting. K2 composition K2. What this is going to give you?
K1.
This is going to give me K1.
K1.
Aha. So this gives me something interesting. What? The cosets which are formed from the normal subgroup, they seem to be closed under all possibilities. That the composition of one coset with another coset is going to give you either this or that. So let me just write down in a neat way, which we call as the Cayley multiplication table. If I write K1, K2, K1, K2. So K1 composition K1 gives you K1.
K.
K1 composition with K2 gives you K2. K2 composition with K1 gives you K1, K2, sorry, and K2 composition with K2 gives you K1. Now look into this. Is it obeying all laws of the group? Is it closed?
Yes, sir. Yes, sir.
Does it have identity?
Yes, sir.
Which one is the identity? Out of K1 and K2,
K1.
which one is that? So
So
K1 is an
K1.
identity,
K-
right? What about the
K1.
inverse of both the one? Do you have inverse of both? K1, of course, it's an identity, so K1 will have its own inverse. What about K2? What is the inverse of K2?
K2.
So K2 itself is the inverse. And you can, of course, I'm not going to go into detail, but you will be able to find out even if you do something like K1, you will always be able to do it this way, which is the associative law, which means that the interesting thing, cosets of a normal subgroup forms a group in itself under coset multiplication or composition. So let me again read it. Cosets of a normal subgroup, remember 1 minus 1 was the normal subgroup, this forms a group in itself under what we call as the coset multiplication. Remember, we defined coset multiplication as the multiplication of all the elements and considering keeping only the distinct elements. So that is how we defined it. This particular group, this is what we call as the factor or quotient subgroup or groups. Now, can you tell me what is the order of this subgroup or the order of the factor subgroup? Order.
So it will be the order of the H only.
Oh, you have seen the Cayley multiplication table, right? What is the Cayley multiplication table tells you about the order? Order of the factor. Yeah, the order of this group where the cosets are considered as an element. So remember, this group is what? It is a group having only two cosets under coset multiplication. So it has how many elements? It has two elements. So now look into the interesting thing again. Order of group was 4. Order of the normal subgroup was 2 in this case. And what is the order which you have got for this quotient group, which is generally written as G colon N. This is the way to write down this one. And this is what? This is nothing but order of G divided by order of N, which means 4 divided by 2, and this will be 2. So order of the factor of or the quotient group of G with respect to normal subgroup N is nothing but mod G over mod N. And it is again, it is writing it like this so that it says that of the group G with respect to subgroup N. Cosets are always made once the subgroup is identified. In this case, we have identified a normal subgroup. So G colon N, this is the reason for choosing this notation, that we are talking about a factor group of G with respect to a normal subgroup N. Questions here? No. Okay. So now I can enlarge my homework which I have given to you. 1. Find normal subgroup or groups of D3. Remember, D3 had 6 elements, and figure out how many normal subgroups you can form out of it. Okay, so you will have to figure out XH time is equal to HX kind of thing. And once you figure out, let's say, one normal subgroup, find quotient or factor group G of n. So basically taking the same thing what we have done here for our D3 group. So we were doing it for a group with 4 elements. Now you try to do it group with 6 elements. And those of you who are interested, of course, you can go further. We are discussing everything about the D4 dihedral group 4 as well. You can try to figure out that. But the coset, the concept of coset has given you two important things in the case of groups. One important thing was the Lagrange theorem, that the order of subgroups can only be the ones which will divide the order of the group completely. And two, that all these cosets will allow you to figure out the normal subgroups and the factor group of that particular group. So the cosets concept has given you two important items of the group theory. Questions here?
Sir,
Yes.
so we read the definition of normal subgroups as G and G inverse, which
Uh,
belongs to
I'm
S
just
can be
coming to
said.
that. I am just coming to that. Have you understood what I have
All right.
said up to now? Have you understand?
Yes.
Okay, it is fine. I mean, what you have read, we will come to that. Of course, we cannot just ignore that. Now, normal subgroups, even though we have looked at it from the point of view of the cosets, but it can be looked at the other point of view also. Why? Let's just think about it. We wrote what? XH is equal to HX, right? Now, if I multiply both sides by X inverse, which has to be an element of the group G, right? So what will happen? It will become XH X inverse is equal to H. So normal subgroup will obey this interesting property as well, that the subgroup will be such that it will also contain elements of the type X, H, X inverse. Or you can take it from the other side also, or you can say it like this. H is equal to X inverse H, X. One way or other, looking into it. Yeah. So normal subgroup will also enjoy this property. And this property is basically what we define in terms of what is called as classes, or also called equivalence classes. So I will come to that. Now, how do we define something what is called the classes? Again, we are talking about classes which will be nothing but part of the group. So we are talking about a group and we are talking about the elements of the group. So let's say G1, G2, G3, so on and so forth. Okay, G3 doesn't look like G3. Yeah. We say two elements G1 and G2 conjugate elements. Conjugate elements. If G inverse G1 G is equal to G2 for, of course, G1, G2, G belonging to G. So somewhere it also has G, let's say. So the two elements of a group G, they are called conjugate elements if G inverse G1 G is equal to G2. So that's what the definition is. In fact, you can relate for this definition from something which we have already done, and let me write down. So this is side note. Do you remember what I have written now? We have done it in something. One of the
Diagonalization.
units. Which unit?
Diagon-
Diagonalization. D is the diagonal matrix. And what was about this P and A and P? This transformation is called as
Similarity.
Similarity.
Similarity
Similarity
transformation.
transformation. Similarity, absolutely right. Similarity, or if the matrix A is a Hermitian matrix, then in that case we also called it unitary transformation, right? Where there exists this. So you can actually look for the similarity which is there, that we are talking about the elements which are related to each other by similarity transformation. And why did we use the word similarity? What was the similarity between D and A?
The eigenvalues are written in terms of
Eigenvalues were identical, basically, right? What else was same? Trace of the matrices were same. What else were same?
Determinant
Determinants
was
of the matrices were same. So the reason why we use the word similarity transformation, that even though the matrix D looks very different from the matrix A, but for all practical purposes, it has all the eigenvalues, the determinants, the traces, which turn out to be same or identical, right? So that is the interesting thing about it. Here we call that if G1 and G2 are related by this relation G inverse G1 G, then we call G1 this. So there is this definition of the conjugacy, or the two elements are said to be conjugate element. Don't worry, we will do one example and hence it will be clear to you. But okay, at this time, it's just something similar to what we did for the similarity transformation. And these kind of elements, so just like D and A here, they can be called as the conjugate elements of each other. That for all practical purposes, for the ones which we are using, they are basically same. Okay, now why this is interesting, let's just continue to work on it. What is interesting further about this transformation is that look into, let's say, so what we wrote as G inverse G1 G is equal to G2. So I can also write it down as, if I want to write down as G1 in terms of G2, what will be this? The first element. Earlier it was G1, so G inverse, sorry, G1, G is equal to G2. So if I want to write down G1, then?
So multiply G
G
inverse
G
on the
G.
left side.
So this will be just this, or I can also write down as this. I mean, it is basically same, right? So you see that if I am saying that G1 is conjugate of G2, then it also means that G2 is conjugate of G1, right? I mean, this is one and the same thing. Not only that, it will also enjoy another interesting property, that if G1 is conjugate of G2 and G2 is conjugate of G3, then it will imply that G1 is conjugate of G3. One can of course check that. Yeah, but what is interesting about it is that group which we divided into cosets earlier can be divided into sets such that all elements of a set are conjugate to each other, but no two elements belonging to different sets are conjugate to each other. So let's just read this definition again, what I have written, that this kind of elements, the conjugate elements, will allow us to divide the group into certain sets, again, not the subgroups, certain sets, such that elements of a given set will contain elements which are conjugate to each other, and no element belonging to different sets are conjugate to each other. That means that if the elements are conjugate to each other, then they will all belong to the same set. And again, I am going to give an example. We are going to do it, so it will be clear to you. Yeah. So this is what we are going to use again to define our normal subgroup. That how group which will be divided into classes, and those classes will be nothing but the conjugacy classes, and those classes can also be used to form the normal subgroup. That is our next step which we are going to do. We have already understood the definition of a normal subgroup from the point of view of coset. Left coset equal to right so coset. We are going to do this thing now from the point of view of the classes. So we'll do it at 2 to 3, I guess. Time is over, right?
Yes, sir.
Yeah,
Yes.
so we will do it between 2 to 3 in that case, that we of course are going to do that. But I will request for one thing from all of you, that try to build your D3 composition table. I will need that D3 composition table from you. Fine. So in order to build these classes for D3 composition table, which I am going to use as an example, I will need your multiplication table for D3, which has the elements E, R square, L1, L2, L3, 6 elements. So please get your D3 composition table ready by 2, and then we will just go ahead, do something for this conjugate sets or the classes, and then understand things. Questions up to now? And then we will basically disperse. None whatsoever. Great. Thank you. So let's meet at 2.
Okay, sir. Thank you.
Yep.
Okay, sir. Thank you.
Yeah.